Okay, we're going to finish our section on factoring by looking at when we factor special case binomials. So this is obviously not always the case, but this can occur in certain cases. So again, we're looking at binomials, factoring binomials after the GCF has been taken out. So these have to be pretty special patterns, and the first pattern we'll look at is what's called the difference of squares. So the difference of two squares occurs when you have two numbers that are perfect squares. So what is a perfect square? Well, 4 is a perfect square, for example, because it is 2 times 2. 9 is a perfect square because it's 3 times 3. X squared is a perfect square because it's x times x. So if you have a squared minus b squared, so two perfect squares, then this will always factor as a minus b and a plus b. So the binomial of second degree power will actually factor into two new binomials, each with degree 1 power. So a very easy factoring technique to do. So let's look at some examples of this. We will remember this formula and really just apply it. So this first one says factor the following completely, x squared minus 49. So the first thing I would of course look for is if there's a greatest common factor. There is not one, because x squared and 49 have nothing in common. So now I would determine, are these perfect squares? Is x squared a perfect square? Well, I would say it is, because x squared is simply x times x. And 49 is a perfect square as well, because I would say it is 7 times 7. So it is both perfect squares, and there's a difference sign. It's very important that it only works when there is subtraction. If there's addition, this does not work. So because these are perfect squares, and there's a difference, this factors as x minus 7, x plus 7. And it doesn't matter the order of the negative 7 and the positive 7. You could just as easily put x plus 7, x minus 7. That would have worked just as well. So that is our factorization. If I want to check it, I could FOIL it. X times x is x squared. X times positive 7 is 7x. Negative 7 times x is negative 7x. And negative 7 times positive 7 is negative 49. Those cancel. There's your x squared minus 49. So really, this is a really easy factoring technique. So now let's look at the second one. So we have 4y squared minus 81. So is 4y squared a perfect square? Well, it is, because 4y squared can be written as 2y times 2y, and 81 can be written as 9 times 9. So these are perfect squares. So they would factor simply as 2y plus 9, 2y minus 9. So that's our factorization. So as long as they're perfect squares, very simple. Now, one thing I did not do on this problem, which I probably should have, was look for a GCF. There was not one. That is not the case in our next problem. If you look at 12 minus 3a, there's a GCF of these two of 3. They're both divisible by 3. So if I take a 3 out, I will have 4 minus a squared. So I should always start with that GCF. Now if I look at what's left in the parentheses, those are perfect squares, because 4 is 2 times 2, a is a times a, so they are perfect squares. So the difference of squares applies, 2 minus a, 2 plus a, and then I'll just put that 3, which was our common factor, out front. Okay, let's look at the next one. Y squared minus 1/25. A little trickier because of the fraction, but these are still both perfect squares, because y squared is y times y, and 1/25 is 1/5 times 1/5. So if I factor this, it is a difference, so y minus 1/5, y plus 1/5. So really just picking out the pattern and applying the rule. Now the last one, x squared plus 25, these are certainly both perfect squares, x times x, 5 times 5, but this is actually not factorable. Now the difference is, this is not a difference, it's a sum. So you cannot factor, there's no factoring of the sum of squares, ever. Only the difference. Okay, let's quickly look at two other types of factoring patterns for binomials. And these are definitely a little trickier. These are what are called the sum and difference of cubes. Now, a cube number, similar to a square number, is a number that is multiplied by something 3 times. So, for example, 8 is a cube number because 8 is 2 times 2 times 2. 64 is a cube number because it's 4 times 4 times 4. So if you have a sum or a difference in this case of cubes, so you can do both in this case, you can factor it. The sum of cubes factoring pattern goes like this. A cubed plus b cubed factors as a plus b, a squared minus ab plus b squared. It's a little more involved in the difference of squares. And the difference of cubes, a cubed minus b cubed, will follow this pattern. A minus b, a squared minus ab, it's plus ab plus b squared. So these patterns are how we would do difference or sum of cubes. So very, very much more complicated, so we'll definitely practice doing some of these type of problems. But we'll remember these two formulas, as they'll really be the basis of how we do these. Now the key to know when it's a cube and when it's a square, well, cubes will almost all the time have something where it's to the third power, like here. So x cubed is a cube because it's x times x times x. 125 is a perfect cube because it is 5 times 5 times 5. So now in our factoring pattern, let's just go ahead and write the rule again. So a cubed plus b cubed will factor as a plus b, a squared minus ab plus b squared. And it is a sum, so we made sure we used the sum formula. So now our x essentially takes the place of our a, and our 5 takes the place of the b. So this will simply factor as x plus 5, x squared minus 5x, plus 5 squared, which is 25. So that is the factorization. This remaining trinomial, this will never factor. So you don't even have to try. I know a lot of times we try to factor trinomials, but this one won't work, so you don't even have to try. So this one is a difference of cubes, namely because it has the difference sign. So it'll work very similar. 27x cubed is a perfect cube because it is 3x, 3x, 3x. And you won't see in this course very many outrageous cubes, so pretty basic ones. And then 1 is, of course, a perfect cube because it's 1 times 1 times 1. So the difference of cubes says it factors as a minus b, a squared plus ab plus b squared. In this case, our a is a 3x and our b is a 1. So we can just kind of follow the pattern. So this will be 3x minus 1. So I'm taking a squared, so I'm taking 3x squared. So 3x times 3x is 9x squared. A lot of people will only put 3x squared and miss that 9. Very important to get that. AB is 3x times 1, so that's 3x. And b squared is 1 squared, so plus 1. So this is the factorization for our difference of cubes. Okay, so now that we have done each factoring pattern, we've done the 4-term, we've done the trinomials, we've done the binomials, now we'll try to put it all together. So for any of these problems, we should of course first look for a greatest common factor. So let's look at this first one. There are 3 terms, but I do not see any GCF between them. So trinomials, remember we factor with our box. So I will put the first term here, which is 4a squared, and I will put the last term in this box, which is 15b squared. So I will multiply the first and the last number, so that's 4 times 15, which is 60. So now I'm going to try to figure out 2 numbers that multiply to 60, but add to negative 16. Now there are a ton of numbers that multiply to 60. 1 and 60, negative 1 and negative 60. But the ones that will work for us are negative 10 and negative 6, because these do multiply to positive 60, but they add to negative 16. So we will put these 2 numbers in our box. So negative 10 and negative 6, doesn't matter where. And instead of just a or x, I'll put ab. And the reason we've not done one quite like this is because the middle term is ab. Everything else will work very similar, but that is one difference in this problem versus any we've done to this point. So now I will factor out of the top row, which I can take out a 2a as the GCF. The bottom row, the first term is negative, so I want to make sure I factor that negative out. I could definitely take a b out, and then 6 and 15 have a GCF number of 3, so negative 3b. Then I will look at the columns. So this column, first term is positive, so don't worry about that. So they both divide by 2, and they both have an a. This one doesn't have a b, this one only has one a, so I can only take out 2a. And the second one, since the first term is negative, I'll take the negative out. 10 and 15 both definitely divide by negative 5. And I'll also take a b out because they both have a b. So my two factors, 2a minus 5b, 2a minus 3b. And of course, if you wanted to check it, we could FOIL it, and we'll check this one. So 2a times 2a is 4a squared. Well, that's good. 2a times negative 3 is negative 6ab. Negative 5 times 2 is negative 10ab. And negative 5b times negative 3b is positive 15b squared. So the check will work because negative 6 and negative 10ab give me negative 16ab plus 15b squared. Exactly what we thought it would be. So that is the correct factorization. Let's look at this one. So the first thing we should still look for is a GCF, and this one does have a GCF. The GCF of this one, they both can divide by 4, and they both have an n. So if I take a 4n out of the first term, I'll be left with 2 n's, so that would be n squared. And if I take a 4 and the 1n out of the last term, I will have 9. So I've taken a GCF out. So now we should look, okay, what's left in this polynomial? Well, it's n squared plus 9. The good or bad news, depending on your perspective, is we're actually done. Because these are both perfect squares, n and n, 9 and 9, or pardon me, 3 and 3, but there are no sum of squares factoring allowed. So we're done. You can't factor it any further. So this would just simply be our answer. So let's look at this one down here, this little two-term binomial. So there is no GCF, because it's x squared and 9. They are both perfect squares, because x squared is x and x, and 9 is 3 and 3. Since there is the difference in this case, we can just do a simple difference of squares. So this would just simply be x minus 3, x plus 3. Okay, let's look at this trinomial. I look for a GCF, and this one actually does have a GCF. Not a variable, because we have s squared, st, and t squared, so none of them have the same variable. But there is a GCF of 3, because they are all divisible by 3. So we'd be left with s squared plus 6st minus 16t squared. Now the remaining polynomial inside, this s squared plus 6st minus 16t squared, looks like something we might be able to factor as a trinomial. It's actually very similar to the first one we did on this page. So we'll try to do our little box and see if we can't factor this trinomial. So this is s squared, this is negative 16t squared. So if I multiply the 1 and the negative 16, that becomes negative 16. So I need two numbers that multiply to negative 16 but add to 6. So the two numbers that multiply to negative 16 but add to 6 would be positive 8 and negative 2. So I'll put 8st like we did above and negative 2st here. So I can take an s out of the first row. The second row I can take a negative 2 out because the first term is negative, so I should always take that negative out. And they also have a t. The first column has an S in common, so I'll take an S out. And the second column has an 8 and a T in common. So my factors are S minus 2T, S plus 8T, with that 3 out in front. Okay, this one is very similar. Let's look at a couple different ones. Let's look at this one, which is a cube problem. Now, I know this is a cube problem, and it is a sum of cubes, because there's a sum, obviously. X times X times X is a perfect cube, and 2y times 2y times 2y is a perfect cube. So if I take my cube formula, which is a plus b, a squared minus ab plus b squared, and that was on the other page. Well, now this is my a, and this is my b. So this is simply x plus 2y. A squared is just x squared, so that's x squared, minus ab, which would just be these two together. So I just like to put it in a little different order, so I'll say 2xy. y2x is also correct. Plus b squared, which is 2y squared. Well, 2y times 2y is 4y squared. So this is my factorization. So let's look at one more. This one is a 4-term polynomial. So this goes back to the stuff we did the very first day on factoring, where if we have 4 terms, we look for a GCF. There is none. So I will take groups of these things and factor by grouping. So the first two, x cubed plus 4x squared, has an x squared in common, which I could take x plus 4. And so the next two, negative 9x and negative 36, they both have 9 in common. But since this first term is negative, in the second one, we always said take the negative out. So negative 9. And that will leave me x plus 4. So now we get these very cool matching binomial factors. So our factorization is going to be x plus 4, x squared minus 9. Because you've got the repeated factor, and then you've got the stuff that was out front. Now this actually can be factored further. Because if you look at this polynomial right here, this is a problem we had earlier on this page. This is difference of squares. So I can actually factor, this is x plus 4, x minus 3, x plus 3. Okay, so we've done a pretty thorough review of factoring. So now, go ahead and try 3-4, assignment 2. And this will be the last assignment before our quiz.